So the first thing is there's a lot of hype about the word AI, ML, and NLP. Today, everybody is thinking AI, but what is AI? So when you think AI, don't overthink it. Just consider it as a field that is trying to provide intelligence. And that's the name, artificial intelligence. So typically, things that you would have done with human intelligence, this field is trying to, okay, you need me to zoom in a little bit more. Okay, I'll do that. Let's see. I think it has a problem. So it's increasing the font for everything else, but not the content of it. Let's see if I write something here. It will look like this. Yeah, hopefully it helps. It's Markdown, so let's switch to the Markdown. Maybe the Markdown itself is better. Yeah, cool. And then we can start with it. So I'm on this point. So when you hear AI, just think of it this way: it's artificial intelligence. So things that you would have done with human intelligence, we are trying to let the computer do that. Things like what? To give an example, to drive a car would require a human to bring in intelligence to drive it, to control the steering wheel, to figure out the gears, to figure out the pedals, to work it out entirely. But now we are bringing AI into that. And some of those activities that required human intelligence are now replaced with a computer or replaced with a digital system doing the entire thing. So when you think AI, it's like a broad field of all of these things where we are trying to replace human intelligence with machine or computer intelligence. Now, how are we achieving that? For us to be able to achieve artificial intelligence, you need to build what we call a model, right? You need to build some sort of algorithm, and that algorithm needs to be smart enough to be able to make the decisions and to be able to do things, to complete tasks, to solve problems. The process of creating that algorithm is what we call machine learning. So the process where we are trying to build that algorithm, so the algorithm has that smartness or that intelligence that we are talking of, is what we call machine learning. Now, remember that I said AI is a broad field. It's solving multiple problems. One of those areas that AI is solving is what we call natural language processing. Because to be able to speak a language requires a lot of intelligence, building the grammar, building the punctuations, understanding them, interpreting them, trying to even talk is a whole field on its own. And the field or the specialized area within AI that is focused on human language is what we call natural language processing, or you may hear people use the NLP like shortcut. So I hope this clarifies like some of the jargons in there. Now, there are other areas that we are trying to apply intelligence, like artificial intelligence. For example, there is the computer vision area, right? Where we're trying to look at, okay, when I take a picture, can we build any intelligence from them, similar to something like doing facial recognition or doing different things? Or it could be when I have an audio file, what sort of intelligence can we build around them? And so we have a lot of like work happening in that area. But irrespective of all of these areas, the process of creating, right, of creating that intelligence or creating the model that is used to bring in all this intelligence is what we call machine learning. Now, for this talk, and probably a future one that is not planned yet, but maybe we'll figure out the planning for that, we're going to focus on natural language. How can I take human language? How do we take human language and bring it to the digital world so we can start building intelligence on top of that, right? And human language is essential because we don't just speak it, but we also write it. So we have a lot of documents or documentation that is referring to stuff that is written, and it will be good to be able to pull all of these to be able to build intelligence on top of that. So let's look at some of the things that we can, why we want to focus a little bit more on, like on the natural language processing bit. Now, the first bit is that NLP is at the core of many modern applications. Today, you have virtual assistants, right? Which is conversation between me and something, like in some digital tool. And how these assistants communicate with me often today is via a chat interface. There are also like the voice interface, right? So I talk, I say stuff to it. It's able to understand what I'm saying, and it's able to reply back to me with something meaningful. Or probably I talk to it or I wrote something to it, and it's able to perform some task for me. The other thing that we've also been using NLP for a lot is sentiment analysis, where you have some text. Let's say you run a shop and you have, let's say, 100, 200, or 1,000 feedback from customers, and you want to know if a feedback from a customer is positive or is negative, right? Or for example, you want to build some sort of sentiment thing, right? Is this going the way I want or not the way I want? And all you have is just text data, right? Or all you have is just human language. How do I take that? That is one area that natural language processing helps a lot. There's also a popular one, which is machine translation, where you take one language and another language and you try to interact between them. So you speak this language, you speak English, and then you get it machine translated into Cree, or you speak Cree and you get it machine translated into English. This is one of the reasons why NLP is becoming very popular, because we're able to relate to some of these use cases. Now, what we talked about is the modern applications that we have around, but then there are also other areas where we as humans want to interact, right, with machines. So we want to be able to not just learn code, because in the past, like for the past 20, 30, 40, 50 years, what everybody had learned is, oh, for you to interact with the computer, you need to write code. So you need to learn a programming language, so the programming language knows how to translate the set of instructions to instructions that the computer, CPU, or whatever can process. But now we don't have to learn programming languages to start providing these instructions to computer in a friendly way, right? So it's kind of like an abstraction on top of what used to be there, but this abstraction is now happening because of the field of NLP, right? And then finally, why we have everybody is all crazy about this is then is the AI booming thing, which I think is a great thing that is happening, right? This X just means I've handled it. So just ignore that. If you see me typing this X in this math, it's nothing. Now, everybody today is using ChatGPT, DeepSeek, Sonnet, whichever like models. And for you to use these models, you need to understand like language. So these models are able to work because at the beginning, when you give them an input, they're able to take your input and they are able to understand that textual information that you have given like to it. And that's how come they work, right? So you can learn how ChatGPT is built without understanding how NLP works, because you need to know how to really parse and convert textual language or like human language to something that a computer understands. And then you can even start building like the extra computations on top of that. So this is like the foundations of pretty much it. I already mentioned a little bit on how NLP relates to AI. It's a subfield of AI. Sorry, let's do this way. So it's a subfield of AI. We are leveraging a number of techniques in NLP to process. I think it's also the deeper, for example, the field of AI is like the broad one, where we do a lot of machine learning. Some NLP task uses machine learning a lot. Some uses deep learning a lot to be able to get things done or to be able to process text or again speech data. So this is something that is like key as well. And then the key part is this one, that you cannot, in the way the world is going, you cannot get to communicate frequently with the machine if there is no way of understanding human language, unless you have to go the older way of using programming language. So now there's a bunch of like foundations in this space. Now I'm covering just foundations here, and we can ignore this list. I'll use the agenda here to make it clear. I just listed 6, but we can go beyond 6 and we can build on this like even deeper. But hopefully we can pick the first 4 today. And if we have more time, we will capture like the remaining 2 and build on top of it. And later in the future, I'll add a few more sessions, which will allow us to dig deeper into this even more, right? So folks can see, okay, now with these foundations, how do these foundations connect with what we know, what we see, or what we interact with, like chat systems and stuff, or even like how do we take this foundation and use this to write like a machine translator, right? How does this work? Okay, so the first thing we're going to be spending some time, and I'm going to be writing code live, so I will just show you guys how to do these sort of things, I will do them in Python. You can watch the recording later, or you can maybe get my notes later, and hopefully that might help. But Python is not the only language you could use, just to be clear. It's one of the most popular languages in this field, but it's not the only language like you can use. What I want you guys to get from this entire talk is, don't worry too much about the language, how to write it, how to do it, but try to build the intuition. Like when you close your eyes, you just want to understand how it works. And that's what I want you guys to focus on today. Build the intuition of how the foundations work. And then once the intuition is there, we can start building on top of it, and then we will build more meaningful stuff. You can find lots of the implementation I'm going to show you on using ChatGPT, Google, Stack Overflow, wherever you want to search. You can find them, so you don't have to memorize them, but just build the intuition and then see how they all relate to each other, and then you should be able to build solutions out of that. So we will first understand what is text data. You all know, but we'll just go through a little bit more and some of the challenges in this. We'll take a look at how we clean up text data a little bit, and then why do we clean up certain things, and what are we trying to achieve by cleaning them up. And then we'll take a look at what we call tokenization. It's a very prominent known term in NLP and even AI, right? So we'll take a look at what it's doing, what it's all about. We'll try to write a few of them. We'll see if we can build some tokens, like write some code to generate some tokens, something very simple. And then there's something called feature engineering. So we spend some time on feature engineering. Feature engineering is a very simple thing. It's all about, okay, I have text. At what point can I feed the text to some sort of machine learning training model for the model to go through, right? And what features is the model going to be looking at to, or the whole ML pipeline going to be focusing on to build like the final model? So we'll take a look at that. And then the other thing is, how do we build a language model? How do we build like a language model and say, this is the model that represents English, or this is the model that represents tree, or like components of all of that. And then if you have some time, we'll take a look at syntax and semantics, and then we'll go through them. I want to go through all of them. Probably I'll do the first 4 today, and then later we can build on top of that. Cool. Any questions so far? Everybody feeling good? Okay, looks like everybody's feeling good. So I don't have any questions. Kathy, would you be asking questions in between, or would you ask questions at the end of it?
They can ask questions in between, and
okay.
Then also leave room for questions towards the end.
Okay, cool, nice. So I'm going to be pausing at certain points, and I'm going to be asking if there are any questions, just so I know I have like a clean like fill of it. So how does it work? So I have a simple Python project setup. It's just a Python setup. What it has is I have like a virtual environment. It's using virtual env. If you know Python, if you don't know Python, don't worry too much about it. But all that I'm saying is I have a bucket where I'm going to be storing all the dependencies I need to finish everything here, right? Now, some of the dependencies I will use, some of the dependencies I won't use. And I will explain when I'm using something versus when I'm not using something. So the core dependencies are all stored in this file called requirements.txt. It's a Python thing, right? Where it says if you have any requirements, you want to put them here, like in this file. So I put some requirements that I have here, and these requirements are essentially packages that has implemented some of the stuff for me. And so I'm just saying I'm going to bring these packages to this project. And when I'm writing the Python code will just have them and will allow me to see all the functionality behind those packages. So these are all popular packages, right? So NLTK, I think I have to fix this sklearn thing, but that's later, I'll do it. NLTK is a very popular Python like library that people can use, and you can take time to go through all of them. I didn't pull Google pages for them, but I'll explain when I'm using them and when not. Some of these packages have the same implementations, or sometimes even the implementation we can write ourselves, but I will try to not do that, and I will try to build some of them if I can. If not, we'll use the packages and then we'll get them going. Okay, cool. Now let's take a look at the first bit. What is text data, right? So when you hear text data, we are thinking unstructured. Let's do this. We are thinking unstructured data, right? Unstructured data means that the data is not structured. So I have no idea of structure for this. Like, let me give you an example of it. So let's say we have a Python variable, and just Python, you don't just write the name of the variable and do equals and just write the value to it if you don't know Python. But let's say I have a variable that says this, right? This is a sample text, right? Let's even add to play with here, right? And I can even make it fun and say my name is Williams, right? If I have this text data, there is nothing I can learn from this, right? There's nothing I know about this. All I know is I have some text, say stuff, but my brain can interpret. But from the computer perspective, I have not given the computer any more information than what I have, right? So we always see that working with text data like this is very challenging. The computer can't do much with it, right? The computer doesn't know nouns, pronouns, whatever. It doesn't know punctuation. It doesn't know. It's like your name is Williams or so. Like the computer doesn't know anything about this, right? So when I look at this from a computer perspective, there is a lot of ambiguity, right? To give it like a very simple example, look at this words like let's call it ambiguous, right? Let's call it like this, right? And let's pick two words. So river, bank manager. I'm using the word bank here and I'm using the word bank here, but the two words have different meanings, right? You have different meanings. So here I'm talking about a riverbank, and all of us can appreciate the meaning behind that. But bank here is referring to an institution, right? A bank manager. It could also be referring to a building, right? So just looking at text data in general, that does not give us a lot of context. So we always say working with text data is very challenging. One of the challenges is that it's very ambiguous, right? So the key thing I want you to kind of like note, and I'll just take points one by one so we can get out of them. So one of them is ambiguity. Now, the second point I want us to focus on when we look at text data is that text data has something we call variability, right? And variability is important because I can also have this text. Let's put it this way. You are good versus you're good. Some people may be slanging the language and they say you're good. Others may also be trying to keep proper English grammar and they are saying you are good, right? Other people may be using the word an and a prefix for certain nouns that do not match understanding for different places. The same word could have a different meaning. Like, for example, if you compare American English and British English, you may hear biscuits versus cookies. And you may be talking roughly about the same thing. But you have these different styles that you can find like in text data, right? So that is what variability is all about. And that's the reason why just working with text data is not really fun. It's another thing that I can also mention, which is also very important. I keep hitting this dot here, is noise. Now, when I look at this text, assuming I'm just trying to build sentiments out of this, right? The point is, how does this dot contribute to a positive sentiment versus a negative sentiment? In general, that is noise. Like, I don't really care about this period in that sentence, right? The word even to may not necessarily be very useful if I'm building, let's say, a spam filter, right? I'm saying this is spam, this is not like non-spam. So in general, like the point should be clear that just working with text data has a number of challenges. There is high dimensionality. You can think of like sentiment and subjectivity, where something is subjective. It's just someone's opinion, and I cannot use that to make a point, right? The computer cannot just learn that and decide that is the right way to do things, right? There is also context, like I did show the example with bank, river bank, and bank manager. And then there is sarcasm and irony, right? You have all those sort of like factors coming in to make it difficult to work with text. So now that we kind of like know what text is all about and the issues with it, there is a need for us to clean text before we start processing it, before we start using it for whatever task we need it for. But before we go into the cleanup, let's try to play with Python if you guys don't know Python, because you may see me do a bunch of some of these things. So if you don't know Python, if I have text like this, there's stuff that you can do. Like for example, you can print. Let's do this in the length. Oh, sorry, AI is going to help me a lot, so that's good. You can print the length of the text by using this length function. You can print, let's say, if you want unique characters, you can print that by using the sets, dropping them all in, and then it will just show me all the unique characters. If I want to see all the words, because it's kind of like this is going to be some of the so let's say words in text. Good. So you can use that. You can pick the text string itself, call the split method on top of it, and then it will show you all the words in here. And if you want to count the total number of words, so let's say total words, you can call the text split, which will give me all the words as an array, and then I can call the length on top of it, and it will just work, right? So if I run this, it will just show me stuff just below here, right? So you see that when we set the length of the text, it's telling me it's 55 characters used in here. If I say show me all the unique characters, for the set, it splits all of them into all the unique characters that I'm using. There's a combination of them. Like for example, there's a T here, there's a T here, there's a T. So you'd only see, sorry, one smaller T, and there's one capital T here, and so you see a capital T, and then these are all the unique characters that I'm using in my text, right? It even has like a space here for, right? And then when you look at the words in the text, you did a split here on the text string, so you see all the words in here. And then if you just put a line on top of it, it counts all of these guys and you get 12. It's just basic Python stuff, right? So this is kind of like what text is all about. Now, I said there are multiple things affecting this, so just keep that in mind. So how do we clean up? How do we make sure the text is ready for processing? Now, there are multiple cleanups that we do. One of them is we do what we call stop word removal. So stop word removal is like saying there are certain words that are common. So they don't add any meaning to a word, right? I can give examples of like those words. The word "the" doesn't really add meaning. Well, it depends on the context, but often it doesn't add meaning. The word "is," the word "in" something, the word "and." For some of the use cases that we use like NLP to solve, they don't really add meaning. So there is like a whole bank of all of these guys that most of the tools will keep. And so you can just tick all of them and you can apply them to your text input and then it will start removing them. Let me show an example so it makes more sense. So there's one of the libraries that I'm going to use, which is the NLTK library. It's a very popular one for learning machine, like for doing machine learning tasks and stuff. So in Python, this is how I just NLTK. I'm just saying bringing this library for me, and NLTK has this corpus thing, and from that corpus I can import their stop words method. Like they have the method that does all of that. Now for me to work, I need to tell NLTK that you should bring in your bank or your group of stop words. So you can see me do this, and then I'm going to download, and specifically I'm going to download the stop words. So I'm saying bring, as part of the NLTK setup here, bring all the stop words that you have behind the scenes. So now let's play with something. So let's say natural. Let's write something. Natural language processing is fascinating. Let's pick something that AI generated for me. That's fine. What are all the words? So first of all, if you were to print what the original words use here, so original words, I showed how that works behind the scenes. Now, what this is going to be, we can do the text dot split, right? So we split the text on space, and it's going to tell me, or like on like, you're just going to pick like every unique word in there, and it's going to show me all the words that I have. If I were to print this and say print length, or let's say count of words in original text, then I can put a line on it, and this will just tell me. And I can just run this like briefly. It needs to run the down thing first a little bit. Let's ignore this one for now. So it will take a little bit of time. It needs to do the downloading. It needs to make sure all the stop words are brought into my computer and all that. But the goal is when I go through this, I'm expecting, yeah. So I'm expecting that unzipping this. You can ignore this red screen. It doesn't mean it's bad. It's just saying it downloaded the package to a certain folder on my computer and it unzipped the whole thing. So this is just telling me that if I look at the original words, I'm getting 18 words being used there. But let's apply the stop word. So, and I know I brought in English, so let's say English stop words. Why am I typing this? Because I imported the stop words here and I've downloaded the full set for English, I can now pick the stop words that I imported and I say, okay, give me all the words in English. And we can print them and you can see them all for yourself, right? So this is the English stop words. And I can show this would be like a full set, a full list of all those words. And if I want to apply it to my text, to do some sort of cleanup, just to give an idea of what people do when they do the cleanup, is I can, so in Python, I'm trying to, you can ignore this. I'm going to break it down. So I'm saying break it into words. So start from this point in this forward E. So I'm saying when you break it, each one is going to be called word. And do this, right? Do the setup here if word or lower is not in this, right? So do all of this, check all of this, check if when I pick each word, if I convert it to like a lowercase and I search through the set of all the available stop words, I can't find it inside it. So this is going to just take my text, compare all of them to the stop words, and if it sees that it's a stop word, it's going to remove them from mine. So if I do a filtered words, it's going to show me this. Now let's run this and see what it's going to show. So the original, you know what? Let's add this print to it to make it like nice, and let's call this count of words after stop words removed. Okay, cool. So you see we have 18, and then we realize that after we apply the standard English stop words bank that the NLTK library is providing, we now have 13 words. So for the actual processing, these are the words that we are going to be using. So for example, if you compare this line and that line, if you compare this with this, you see natural is not a stop word, language is not a stop word, processing is not, but is and it's these, both of them are stop words. So they were not captured after the filtering, right? And then we focus on fascinating, focus on field, off, study, and then we pick the rest. And then other things I'll show you. So this one sort of processing that is done to the string, because for some use cases, you just know that the word does not contribute to anything, right? It does not help. So it's good to have these stop words bank, always rely on them so you can clean out some of these things. Now, there are use cases where it's not good to do this. Like, let me give an example of a use case. Let's say you are building some sort of solution that is able to figure out the parts of speech to a word. In that scenario, you care about every single token, or you care about every single word, every single component, like inside it, right? So you can't necessarily remove them, right? You need them, right? So even though we use these standard stop words, we're not saying we want to use them all the time. I would say you need to know what use case you are solving for, and if the list in the stop words bank is useful for you or not. And if you think the list is not useful for you, you can filter that a little bit more so you have your own set that works for you, and then you can use that to clean. Before I move on to another cleanup flow, any questions? I can't see the chat, so if there are questions, someone should maybe coffee or the moderator should just jump in.
Yeah, there's a question, but Audrey, do you want to turn on your mic and ask the question directly? We want engagement. If not,
Hello?
I'll just. Okay, she's here. Yeah, go on.
I think you must have answered the question to some extent. I was asking who determines the English word and how, whether it was context specific or generic.
Yeah, it's generic. So you can see the list here. So it's a generic term. Like, so from studies, folks have tried to build stop words. So this stop words that I'm showing is the one provided as part of the NLTK. It doesn't mean the same set of stop words may be used in all other libraries. May not, right? You could also have your own stop words. So it's not a rigid set that everybody has to use it. Like for English processing, you choose how you want to do that. But the principle is what I want you guys to get. Like the principle is there is a like you need to clean up your text. And if there are components or there are tokens in the text that do not contribute to the solution you're trying to build, then it doesn't make sense to keep them as part of the text that you are going to be processing. So as part of pre-processing, as part of cleanup, you want to remove all of this. Cool. One of the reasons why stop words are also very good. Okay. Very nice. Good, that answered the question. One of the reasons why stop words removal is also very good is that it also helps with the processing speed, right? So if let's say we were to use the original text that had 18 characters for future processing, and that future processing considered each word, it means that I now need to, that future processing, whatever algorithm we will use, has to look at 18 words. But now we are making it look at 13, right? So 13 makes it easier and it's able to process faster. It also helps with like improving the accuracy of it, because if a word is not needed, then we don't need to build a dimensional, like we don't need to think about it whilst we are going through the actual processing. So we can just take it out and it's no more considered as part of it. So that's kind of like why what stop words is trying to solve here. And it's one of the popular cleanup techniques that you want to always keep in mind. Any questions? Or should we move on? Cool. Okay, sounds like everybody's good. Okay, cool. There's another cleanup process that is very popular, and I want to mention that a little bit. We call that, and I'll do this to make my Python code looks good. I'll just do this. So let's. Oh, yeah. So type more. Okay, I type more. Cool. Let's scroll down, and it's what we call. Let's do this. It's lemma, right? We call them lemmatization and stemming, right? Or like stemming and stemming, right? Now, what are these? So there is actually, let's talk about stemming first, because stemming is like the easiest one to understand. So, oh, great, nice. I'll bring this up and see if it makes sense. So stemming, it says it reduces a word to their root words. And the reason why we need this is consider the word this. Let's put this one. It's a very good example. If I have the word running, and I also have the word run, right? For stemming, both of them are going to give me run. So I don't have to worry about the ing versions or the different states that the word can be in. I don't have to worry about that. So that's a very good, that's one of the things that we want to also think about, was if we don't do this cleanup, then the further processing is now going to focus on, oh, it's going to treat running separately from run, R-U-N, and separately from run, R-A-N. However, there's a clear difference between a stemmer and a lemma, or the stemming and the lemma. This one reduces it to the root form, which means it will strip down ing, and maybe we'll figure out we need to clean up this n, right, at the end. But if you have certain words where lemma comes in, for example, if I have this word better, it may stem it, if I were to use just stemming, it may get it down to, let's say, bets, because it's just removing er. But if I'm doing lemma will bring the word down to the root version or the base version that can be found in the dictionary. So that better will return good for lemma or for lemmatization, but it probably will give us something else when we go through the stemming. Just to make it like easier for people to absorb, let's try to bring in that so we can play with it a little bit more, right? So NLTK has something around stem, and we can import it. I think we just need the proto stemmer. Let's see if we can do the, we have the word lemma, so we can use both of them and then play through. We will use the word better as an example, right? So what we want to say is, let's create a stemmer for now. We're just calling the portal stemming thing that we brought in. What is it saying? Oh, I got it. Yep. And then if we were to say, I'll just do this one, and then I will pick my, if we were to say, pick all the words that we filtered out, the ones that we processed, if we were to say, pick all of them and run them through, yeah, tell me the same thing again. Okay, cool. Run them through a stem. You know what, let's make this simple. Like, wise. Let's say stemmer.stem. Let's put the word, let's do number one. Let's put the word better in there, right? And then if we run this, let's see what it's going to tell us as the, oh, I didn't, sorry, I forgot to do this. Stem word for better. Typing too quick. Yep, and let's do this. And then we'll do the lemma as well. So you see, I'm stemming it, which is supposed to reduce it. It's saying I can't do anything. But let's try to see if we were to do the same thing on the lemmatizer, right? Using the like. So let's pick the word in lemma that I draw, like word like lemma that I'm drawing, and then let's have a lem token, which is using this. And let's do the same thing for the word better, and test and see what it's going to show us. Oh, so this is not a good one. It should actually, so it means that like this needs some help there as well. But let's pick the word going as an example for the lemma. This needs some help. We probably would not use this for production. We probably will use something else. Let's say this going. I'm typing very inefficiently, but let's see if it works. To just left with the point. So the stemming removed the ing and went with go, but the lemmatizer said no. I still feel like we should keep the word going as the lem for that. It's fine, but like the point I'm trying to bring up here is you want to pick one of them, and usually people pick like the lemmatizer because you want to standardize all the words to like a base form and be able to use that base form through your processing. Now, there is a lot of advantage to doing this because you don't have to work with a high dimensionality. Like you don't have to work with multiple dimensions of the same word, treating all of them separate, right? You probably be thinking of one word or just one expression, and you'll be using that same expression when like you go through the entire. Let's try with the word running, just to nail the points. And I'm curious what running will show myself. I probably should. Okay, so yeah, so stemming is removing the ing. Lemma is saying nope. I think there's a base form called running in the English dictionary, so it's trying to work through it. We could have also passed the entire filtered list through it, and that probably would also have like work as well to tell us what is the base form for all of this, and we can move on from that. Any question? Sorry, any questions so far before we move on? Okay, sounds like a quite good. Does it make sense? Or can you guys not hear me? Okay, cool. I'm seeing thumbs up. So it looks like everybody can hear me and probably see me. Okay, good. Yeah. It's a lot of information, but I'm trying to go as slow as possible so folks can get the whole picture, right? So let's reiterate. We need to do processing. Like when I have text data, the computer is not able to process the whole thing. But before you even worry about the computer part of it, we need to make sure that relevant words are used, irrelevant words are taken out. Or to even do it like in a very, like to say it in a different way, relevant context is only preserved, irrelevant context is removed. If that irrelevant context is the removal of punctuations, then remove it, right? Remove all the punctuations from it. If it means trying to use like a lemmatizer, so you have the lem token or stemming like algorithm, so you have like a stem as your base form, then go with it because it would reduce the dimensions that you have to worry about. will standardize everything, and then you can now take that to the next step. There are also practical things that you can do. So for example, you have a business, and in your business, you know specifically what you want to do. So let's say in your business, you have specific keywords that you've been using, and you have a list of all those keywords, and all you want is you want to be able to take like a full text and you want to extract and see if any of those things that you have as keywords exist in it. Then you can also like extract all of them from a sentence, see which ones you have and work with them. And sometimes like these tools from the libraries don't help. So you could also use like regular expressions, and I'll just type them here just to make my life easier. So for example, you could use Python regular expressions, whatever language, programming language you have, you could use regular expressions and just make it work, right? So let me give an example of what I mean by you could use regular expressions here is, let's say I'm looking for specific words. I'm looking for the word, let's say I'm looking for the word fascinating in this text, right? So what we could say is we could create a pattern, right? And in my pattern, I'm just saying I'm looking for the word fascinating. Oh, is this an S I miss? I'm looking for the word fascinating, right? So if I find the word fascinating, that is what I'm looking for. To see if I can find it from the texts, right? We can use regular expression, and then we can search through. So we can give a pattern, and we can tell it that's a text I want to find. And in Python, I can say if you find that, then tell us you found that text in the pattern, right? And then else, just say I did not find that text. It's up to you. You have all the control you want to do. And regular expressions can be as complicated as looking for words. It can be as complicated as looking ahead of words, looking behind words, trying to see patterns. It can be as complicated as you want. If you think that will help you solve the use case you are dealing with, right? So in this case, find it, right? It's up to us. And you could do anything that you need to work with. The core point, like the key points I want to like highlight over and over and over and over again is that once we do this cleanup, there are very clear benefits that we get, and we need those benefits to allow us not to do sharp. So let's do this. So let's say benefits of text cleanup. One of them is we improve the accuracy because we don't have irrelevant context moving. So if we only focus on the right things, and if the right things are coming up, then we will build models, we'll build solutions, we'll solve things on the right input, right? The second thing, let's see if it reduces noise, like, so irrelevant context shouldn't be brought in, it's irrelevant. I wouldn't worry about this, but I would probably put this here, and this will be, it reduces, yeah, it's almost similar to this, but for dimensions, for example, the word go, going, went, and all of that, like you can reduce all of them to just one word, so that if you care about the word, let's say happy, as a way to build a sentiment analysis to show positive sentiment, you don't have to worry about happy, happiness, joy. Like you can just simplify all of them to just one thing, right? And then stuff like if you're using the word laugh, laughing, laughed, all of them could just be condensed into just one base form, and that base form will be used in your further processing, right? And we've talked about at least 3 techniques that you can use for text cleanup. We talked about the stop word removal. So some words you think, yeah, just get them out. We talked about the stemming approach, where we reduce the words to their base or true form, so we can remove the ings in some other forms that the stemmers often do. Talked about the lemmatization, bringing it down to its base form as you can see it in the dictionary. So we take the word and say, okay, what is the base form that I can get to the dictionary, like with you can get it down there. And you can also we talked about using regular expressions, where you can do whatever you want. Regular expressions, you can build your own patterns, and you can start applying these patterns to your text. Okay, I've tried to reiterate over and over and over again. Cool. Any questions, concerns, thoughts? Yeah, Audrey.
I remember you said something regarding punctuation in your delivery, but I didn't quite get that. I want to know if it's necessary to remove punctuation while cleaning, and if there are cases where it's advisable to keep punctuation.
Yeah, so Good question, actually. So yes, sometimes you don't care about punctuation. Like, to give an example, let me use the sentiment analysis thing again. So I have reviews from people, and I'm trying to check if the review is good or bad. Let's assume that the approach that I'm going with is I have a set of words that I'm looking for in English that gives positive vibes, right? And so I'm looking for those words. Now, what is going to happen is that if I do, let's try to explain with, so watch this a little bit more. I'll rerun this again. Watch this word a little bit more. You see this word study with the period there, when it was splitting into words, it added it. Is that really helpful? I don't know if you get my point. Is that really helpful? The answer is no. I don't need to have a word that has a period at the end as part of my keys, like as part of my processing. I want just the word as my token, and I want to keep my word the way it is, right? In such a scenario, it will be good for me to clean up this and remove all punctuations, because they don't add any meaning to the example I gave you about sentence, and I'm looking for specific words or specific signals, right? So if somebody said, I hate the food, the period at the end doesn't add anything. Question marks, exclamations doesn't add. Just seeing the word hate is enough for me to give a negative sentiment. So because of that, punctuations do not make sense. However, let's say I was building something where I want to analyze the tree language or the Hausa language, right? And I want to analyze the parts of speech or how each word relates to the other. Perhaps with the parts of speech, I would want to know when a sentence actually ended. So even though I may not necessarily pass period into my algorithm, I need the period or the full stop somewhere in my processing to indicate that a sentence has ended. Right? You could do a split on the period, so you have all the individual sentences, and then you can pick each sentence without the period to further process, or you could do something else, right? Or you could pick any of the punctuation marks, like question mark, exclamation. You could pick some of those ones. So it depends on your use case, and your use case will tell you whether you need them or you don't need them.
All right.
Okay.
Thank you.
Okay. Cool. Any more questions? This is gonna get a little bit. It's gonna get a little bit complicated. So I'm going to give folks a few seconds. Any more questions as you like condense and like as you try to absorb what we've just talked about? Okay, good. Okay, cool. I'm going to take it as we are good. Everybody feels happy about this. Cool. So let's move on to tokenization. So what tokenization is actually solving is now that we have like we understand that we need to remove stuff that are irrelevant from the text we have. We need to clean it up. We've talked about some techniques you can do it. We now have to figure out how are we going to provide the inputs to the computer, like for processing. The true fact is you have to figure out how you want to break the text down, right? So you can't just feed the entire sentence into the computer because that's a lot of information, right? Sometimes you do, but for most cases on NLP, you want to learn how can I break things apart, right? So you can break things apart by using by focusing on each word. You can break things apart by focusing on each sentence. You can break things apart by using each character. And if you want to learn how OpenAI and some of these big AI companies they work, they do not go through any of this, but they break things apart by what they call subword tokenization. So let me list the techniques that I mentioned. Okay, so we have word level, we have sentence level, we have character level, and then we have what we call subword level. This like more advanced, right? Maybe someday I'll spend some time and show you guys how to build that, how to use that algorithm to help with some of the stuff. And often we use subword tokenization in like in neural networks. neural networks is part of like a field, like we normally talk about neural networks like for deep learning stuff, where you want to like learn deeper and go deeper into like some of those machine learning or even AI concept, right? So we will keep that out of context for today. But just to keep in mind, you decide how you want to break things apart. You can do word, you can do sentence, you can do character, you can do subword tokenization. There are studies even figuring out, like even on the subword, there are studies even figuring out how to improve it as well. I've also seen others also around sentence, around like even trying to figure out how to take a sentence and tokenize it and go deeper. But for now, when you think tokenization, don't worry about the advanced concept. Just think of it like I have text. I want to break them down into smaller units that I can work with. Before I move on, let me talk through some of the applications, like how we can apply this technique. Like, why are we doing it? What are we trying to achieve here, right? So let's say we are doing a spam detector, right? We are building a spam detector. Now, to build a spam detector, you could have, there are multiple ways to do it, but let's say one way we chose to go for is, I am looking for specific keywords, and if I see a number of them, I assume that that email is a spam. So for me to be able to do that, I can split on the word level, and I can be doing comparisons with my spam checklist, just making sure that the spam check, like the word is not in that spam list. And if I find some of them in that spam list, then I know that it's a spam, and I flag the entire email as a spam, right? So that's how my algorithm is going to be like. In that case, a word level makes sense, right? It could also be that I'm doing like topic labeling. So I want to figure out what an entire sentence is about. One way, or even an entire copy, an entire like paragraph, an entire like document is all about. One way to do it is by looking at each word and trying to reason on each word. And then if I see another version of that word coming in, I can try to coordinate it and then figure out, oh, I think it's the same thing. I think it's about this topic. Or I can even pick a word and figure out how often that word is repeated within the entire corpus, the entire document. Then I can make a decision on that. And that word character, like sentence, word level tokenization might be helpful, right? Or let's say I'm even building like an NER, like a named entity recognizer, right? Those work like, I can take a sentence and I can tell you what each component represents. So I can tell you in your sentence, I see a name of a place, or I see an address, and I can tell you where that address or the name of a place is, like within that sentence. In that case, word level stuff can also be very relevant, right? But sometimes I also need the entire sentence. Like I want to see the entire thing, right? There are also use cases where both word and sentence are used. One example of where you need on the word level or close to word level, or it used to be at least a few years ago, it's like machine translation. If I'm trying to translate something, I don't want to be seeing piece of it, because, for example, in one language, you may express a thought with 3 words. In another language, the same thoughts can be expressed with just a single word or just 2. So if I were to take in word level, word at a time, and I try to do word for word translations, that might not work, right? So I need to see the full sentence. So I need to be able to chunk in and tokenize or think around tokenization on the sentence level. And then once I have that and I see the full thing, I can now make a decision as to how the translation should work, or how I want to train like for that one. So there are use cases for either of these, right? And the thing is, don't always say one is the go-to approach. Always look at your use case, think a little bit about how your use case is working, and then you can figure out the right tokenization technique, or the right tokenization thing to bring in. Okay, cool. Now let's get through some stuff so you can visualize how this happens, and yeah, how we can do these sort of things. So NLTK has stuff that I can use. So there are 2 libraries that I like using a lot for tokenization. One, my favorite is Spacey. I love it so much. Spacey is like a language model. I'll show you guys later, but let's start with the simple one, NLTK. So with NLTK, we need to tell it to bring in what they call the punct. It has like the tokenizers in there. So it has the English one. So we'll just tell it to bring it in. And then we can also, so you know what, I can just say from NLTK, switch this. And I think we have the word, yeah, it's there. word tokenize, and then I think it also has sentence tokenizer. So I have a bunch of this, and I need to do important so I can get there without them working. And so let's pick some text so we can tokenize. Let's pick the same text we use. So if you want to see the word tokenizers as an example, word tokenizers. So we can use the word tokenize, passing this text, it will tell us all of them. And if you want to do sentence tokenizers, it's going to give me the exact same thing, like, pretty much, because I have just one sentence. But we'll see whatever transfer. Okay, so you see the words, all it did is what it splits. Now look at something interesting it did. You remember I raised a problem where I said study with a dot. When we were doing our manual thing, the dot was in there. See what it did here. So the words, it does study, and then it does the period separately. So these tokenizers have been trained to work with the punctuations. They know they have to separate the punctuations from the words they follow and isolate them. So it's easy to work with these libraries, unless you want to build your own. And then you see when I did the sentence tokenizing, for now, I have one sentence that ends here on this period, and then it involves will be like another sentence that comes in separate entry. So I have like an array of 2, and the other one I have an array of this. So far, any questions? If I want to do like character tokenization, I don't necessarily need this. I can just do this. You can use Python because it's just every character, so I don't need this. So if I do, I can just drop the entire text into a list, and then it will split everything into their own characters, right? So I don't necessarily need a tool to do that. Cool. Any questions so far on the idea behind tokenization? Yeah. So
Just to confirm, if we're doing this practically, we would have to use the text cleanup to remove the stop words before moving to this step.
Yes, preferably.
Okay.
Yeah. So practically, you have to remove stop words if you think stop words are like not needed, and then you bring in your tokenizing. Like you break it down to your individual tokens. Yeah, and then you're good. Cool. Any questions? Audrey.
I'm wondering how the word tokenized method works. I used to think it's splitting based on white space. So after every white space it's split. But from the way it splits study and then the period, I'm questioning that. So
Yes.
is there a logic? What logic is it following to split the word?
Yeah, you might want to look at the library's implementation of that. But the point is, just splitting on white space is not enough. You need to always worry about punctuations. There are also dashes that may appear between certain things, right? Some words will have a dash, like together. You have an English. Let's say I try to do this. Let me just play with some Ghanaian names and see. It's been a while since I did that. So let's see. Now we should like this, right? Now do this. Like this one. Let's run this again. You see, it knows that this is one word, right? It knows that this is one word. But let's try with something like this. Good stuff. It knows that this part is not one word, right? But it will give you this and then give you the separate ones and make sure the period and all the other punctuation afterwards is handled separately. The idea is you can't just rely on white space. You need to rely on a bunch of things. You need to rely on punctuations. You need to rely on other things that the language may have. So some languages have their own things, right, that are unique. Like, some languages may have certain accents, certain things on words, certain things that denote end of sentence, right, without necessarily using a period, or like crosses over one snare to another. So the language will tell a lot about what to do. But don't just rely on white space stuff, like to do these sort of things.
Okay. Thanks.
Cool. Any more questions? Okay, cool. Now, all we've done at this point, even until the word tokenization is a little bit like it's used loosely in this context. In actual programming, like so natural like machine learning terms, tokenizers generates something else, not just words, right? So even though I'm using the word tokenizer, right? And I'm showing you guys it's returning words. The computer does not understand words. Like, if you give CPU words, it's not like there's no way CPU can interpret words. The computer understands numbers. So all of the things that we've been talking about is we would need to find a way to get it to be a number at some point. We cannot work with words, right? So, and that's what feature engineering is mostly about. So we need to figure out, okay, what are the most important pieces? So now we know how to clean up the text, how to break it down into certain tokens. I'm using the word tokens meaning certain components or certain pieces of the unit. But the point is, how do we now take this and bring it into how do I take this and bring it into the computer so the computer can actually do stuff? Let's see if I have to get this. Yeah, but I'll figure the sklearn thing right now. I think I need to do this. This is sklearn. I think this is the word I need. I think that's what I need to do. Let's see if I'm getting it correct. We'll see if it's bringing up. Let me see aside. Oh, you know what I'm doing? I'm doing something stupid. Yeah, that's why. That's why it wasn't working. I was like, what am I typing there? Okay, so sklearn is written by the scikit team. It's part of this scikit-learn. It's like a kit full of like a number of things. So I was like, what am I doing? Okay, cool. We should be good at this point. So let's come back to feature engineering. So what I'm saying is feature engineering is we need to figure out, now I have like what I have, but how do I take what I have and how do I send it to the computer, right? Now, there are a number of techniques that can help us convert what we have into numbers. But before we even worry about the numbers or the integer bits behind this, we need to ask ourselves, how do we want our tokens to be preserved or used? So let's say we did like a word token, right? A word tokenizer, right? So we split everything into like words. We have 10 words to work with. Do we care about the order or do we not care about the order? Maybe if we are doing sentence analysis, we don't necessarily care about the order in which the words appear. We just care that a word is in there. So in that sense, the order doesn't matter. Like sometimes we care about how often a word is used in a space, right? Or how rare the word is. And then just that component informs us on how we want to actually think of that, right? So these are all key things I just want to mention now. So let's dig into some of the like the ways to do this. So the first one we want to do is, if I don't care about order and all I care about is the tokens I want to use, bring them all together, then we could use what we call the bag of words, right? And like the name says, it's a bag. We create some sort of a bag full of words. So a bag or some sort of container, and in that container, all that we can find is just words, like word one, word two, word, whatever like the word is. And then we take all of that through our processing and say, these are the words you want to think of, and then we just build it like based on that. But if I care about the frequency in which, actually it's the name I'm looking for. If I care about order to a degree, or I care about how rare, like if I care about some of these things like order and like not necessarily like the right order, but like the frequency of certain words within a space, then I need to use TF-IDF, right? If I really want to build some sort of a model that understands words and their relationship, then I could do word embeddings, right? And there are a number of them. There's by Google, there's by like Stanford or so, and there are others like that we could use. Actually, OpenAI also have their own like word embeddings that you can also like embedding library that you can use. Or or we could even use stuff like what we call the BERTs. BERT embeddings. Like BERT is bidirectional something. It's based on the transformer technology. It's also used to help us build this. We'll get through that like in time. Let's pick them one at a time. So let's take bag of words, right? So the bag of words is that we know we have a bag or a container, and then we have words in that container, and we just want to achieve three things. So the goal is we want to do the tokenization as we have, and then we want to build a dictionary, and then we just want to create a bag, or what we call the vectorizer. Like we want to create a vector. Like, want to just say, this is all that is in there. It's simple, it's efficient, like it's quick. It gives you a baseline. You don't have to do anything complex, right? Those are like good things you learn from this. But it also can lose context because it doesn't care about the order in which the words are coming in, right? So you lose the context. It also is like the dimensionality is also very high, because what it needs to do is it needs to figure out the book. It needs to go through each word and build a vocabulary set. And then it's also very sparse as well. I'll show you like a very good way to visualize the bag of words. So let's start with that one. So let's create a document. Let's put documents so I can get like a list of them. Let's see if Copilot can give me stuff. Let's put this one. Okay. Okay, let's put this one. Let's say I care about, let's put AI here, it's fine. And machine learning. Right? So let's say I have a document, and I'm intentionally splitting the document into multiple like sentences, or what I'm going to call. So this whole thing, document, you often see people call this expression corpus. It's just saying it's my full data set, like all the data I'm working with here, right? We can bring in sklearn because it has some of the tooling that we want to use from this. So let's say sklearn. I think sklearn feature extraction, we can import. Let's pick one of the feature extraction ones. Let's pick the one for text. We can import account vectorizer. I'll keep this guy here because I'll use it also for the second line scenario. So what we are calling the vectorizer here is essentially what I'm calling the bag of words, right? It's essentially that, right? It's like the algorithm to help me create a bag of words. So once you are done, you will give me some sort of a matrix or some sort of numerical representation of it. I pick my vectorizer and then I fit, like I'm saying, take my entire data set, my list of sentences that I have, which makes up my document or my data set, put them into this algorithm or whatever we have. Put them into the algorithm to see if you can generate bag of words for each of my sentences. Once this is done, I will have bag of words, which we call BOW. Often you hear people use that a lot. And then all that this is doing is taking the matrix, like after passing this through that vectorizer. You can write this vectorizer from scratch to look at the code that is ready. It's very simple. But put them through it and convert them into an array so I can see what each sentence is mapped to. There are a few key things to keep in mind. Let's print this example. And then let's put bag of words. Right. And when this worked, there is something we can also do. We can ask ourselves, what is the vocabulary set? Let's create it. I think we can pick our vectorizer and get, yeah, that's right. Nice. Okay, now this is interesting. Like, why am I seeing zeros and ones? And like I said, that's because the computer doesn't understand words. So it just understands numbers. So we need to make sure what we have can be converted into a number, a numerical set, and then we can take that numerical matrix into the computer for processing, into the next stages for processing. Now, how is it coming up with zeros and ones? The first thing it did was it tried to convert every word here into this vocabulary. So it's saying in my corpus or in my documents, right, I have these words that I'm using, right? And you may have noticed something, right? Like natural started with the caps in, but it's realized that doing everything in a lowercase is good because then it will be able to at least preserve some meaning. So this is my entire vocabulary set that the vectorizer or like the algorithm we are using for bag of words that it created for us. Now, this sentence has 1, 2, 3, 4, 5, 6, 7, right? It has 7 words. But if you look at what was generated for it, it's more than 7 because it tried to standardize on the longest sentence. And then afterwards, all it had to do was, okay, build this bag of words in here. So you have one. Let's look at the vocabulary set. I think that will help make this. Let's do this size of vocabulary. If we fix this, it's like saying that we have 21. So we expect that each one has 21. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, right? So it's trying to say each sentence should be of 21 tokens, right? Of 21 entries, right? Let's put it that way. And in this 21, the first one is about. I think the first one is about 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Fascinating. Let's see. 1, 2, 3, 4, 5, 6. So fascinating is on that seed position, right? So it's saying that I found this is 1 on that seed position. Filled was next to it, so filled was 1 here. The next one after filled was off, so generating was 0, and it will find the exact spot where each of those words appear in the vocabulary, and it will mark them as 1 and 0. Does this algorithm make sense to everybody? Or questions here before I move on? It gets funky. Okay, cool. Everybody's saying yeah, good. Give me a sec to fix something that just turned. Just give me a sec. I'll join you guys soon. Okay, sorry, I'm back. The camera is not working now. Okay, it probably will work at some point. Okay, cool. So what it's trying to do, like I tried to explain earlier, was we will build a vocabulary at some point. So it tokenizes each one into words. So it splits everything here into a complete set of words. Use that to build a vocabulary, which is what you see down here, as we were seeing. And then the size of the vocabulary will become the dimension that is represented by each sentence. So each sentence will represent this by the size of the vocabulary. So in this case, our vocabulary has 21 items in it. So the size that we are going to represent here is going to be 21, right? And then the vocabulary, we're going to be matching and saying, do I see the word about in? Do I see the word AI? Do I see the word this? Do I see the word that? And it will just keep matching until it's able to build the full bag of words representing that. Now, is this good? It depends. Sometimes this is enough. But you may have realized by looking at this that if the vocabulary size is large, like assuming we had the entire English dictionary to consider, then my dimension will probably be in the thousands or tens of thousands, right? Because the English vocabulary size is really large, right? It's going to be like in thousands. It means that I'm already allocating like a spot for 1,000 for each sentence that I'm going to be processing. That's not really, really effective. The second thing, and that's what we call like, it will be like a high dimensional, like I'm working with a very large dimension, right? Dimension size. Second thing is that you will see that it's possible that if I had like a short sentence like this, hi, as an example, you'll see that most components is going to be zeros, right? Like hi, all of this is 0, all of that is 0. And I just raised the size of the vocabulary to 22, right? So that's also not necessarily good. The other thing that I also mentioned, which is not good when it comes to the bag of words, it's like a con to it, is it built this matrix based on the vocabulary and not based on the order in which words were presented. So if we wanted to build some processing based on the order, it's not going to help us. It's effectively useless, right? I can't use this approach for that. So what would bag of words be useful? If you want something very quick, something very fast, if your dimension size is very small, or at least can be compressed to somewhere in the hundreds, or even lower if possible, then it's like a quick and fast way to do it. If you don't care about the order in which words appear, then bag of words becomes like something you can consider using as some of your feature engineering. Like you could try to convert your text or your corpus into the bag of words count, like vector or matrix, and then you could use that for further processing. Any questions so far? Okay, sounds like folks are good. Coffee, do you have any question in the chat?
No questions.
Good. Yeah, it's getting technical, but I know. But the key point is, remember, the computer doesn't understand words. So after all the pre-processing we've done to clean it up, to make sure it's in good shape and all of that, we need to take that output and we now need to token, like we need to create actual features that we can work with. So a feature is the expression to say, what should be the shape we want to take the data before processing it. Right? Just like feature engineering that we are doing. And we're actually creating vectors, or like, yeah, we can also talk of this as our tokens, or we are representing our tokens like for feature engineering. Okay, now I brought in another algorithm, which is the TF-IDF. Now, TF-IDF is a little bit different. This one, which is the term frequency inverse document, it's different from bag of words in that it takes into account the importance of each word as related to the entire document. So if your algorithm cares about words and the importance, like for example, if you're building a spam filter where you care about specific words and you want that to be used or to be considered, then TF-IDF could be like a very good one, right? Assuming your vocabulary size is also very small. Let's see an example of the same thing that we did, what TF-IDF is going to bring, right? So if I did TF, I will need to create, so I call this vectorizer. So this is going to be, let's call this TF vectorizer. And I already brought in the vectorizer. I already imported. So this imports is coming. I'm using sklearn. It has like some of these things from the feature extraction stuff. So I'm using this one. So I already have that there. Let's get some space for ourselves. And then let's look at our matrix. Hold on. Let's call this one TF matrix, so I can fit this entire matrix into it. And then we can now start printing stuff. Okay, let's print stuff. You know what? Let's bring this to the face sounds like. Okay, so let's print stuff. And then, so this is our matrix. There we go. And this is our entire TF-IDF thing. And if you want to see its vocabulary sets, let's pick its vocabulary sets. It's likely going to be the same or not. We'll see. So the vocabulary sets is almost the same. It ends with using, starts with about. If you scroll up, ignore these numbers for now. Starts with about, ends with using. It's almost the same vocabulary set we are working with. But you will see that it's different. Now it's not just zeros and ones, like a 0 and a 1 flip, but then I'm getting what we call weights, right? Weights being assigned to specific numbers. It still has the same dimension that we were dealing with. So for example, one sentence will run from here to here. I still have 1, 2, 3, 4, 5, 6. So 6 on 1, 2, 3 will be like 18 or something. And then it's not like 22, right? It's not the same 22, similar to what we were doing with bag of words. But now all the ones have now turned to weight. There is a 0.36 and there is a 0.28. And if we had a bigger corpus where certain words appeared or changed, for example, if I were to do this, hi, and I build more on this, right? Natural language processing is great stuff, right? Oh, sorry, put an R here. And I would even do this, and we can find the spot for N for natural, in the center at the bottom, the weights will start changing slightly. So if you can see, the weight is starting to change, and some things is going to change. I can work with the weight. See here, so I can get like the word for processing coming up. Yeah, the weight is going to change, and it's going to be adjusting to this, right? So time frequency is useful if you want to take into account the importance of each word. Like, okay, so I want to see the importance of each word in relation to its context, in relation to the entire document, and to be able to build specific weights based on that. But it has the same problem or some problems similar to the bag of words. It's still going to work with, it's still going to be sparse, right? Some of them are going to still be zero. Like you still see the zero is not going. I'm just having them in floats, but the zero is still there. So I still have them. The only thing that's changed is I don't have just one, but I have higher and lower weights. And so if we start training or we start using this for something else, like in the future, the numbers will mean like two things will not mean the same, but they will mean differently based on the weights assigned to them. However, I still have to deal with the zeros. I still have to deal with the same dimension size that I'm working with. That's 22. Like as I increase the vocabulary size, it's also going to increase. It doesn't know context as well. So it does not capture the semantics. So for this, it thinks each word is the same, and it's just looking at, okay, how sparse or what's the frequency of the word, and like in its context, what's the frequency of the word in the entire document. It's still lacking that context, or what we call semantics, meaning behind words. But it's just treating each other the same and trying to use the same algorithm to compute. If you want to build something that doesn't care about the meaning behind the word, but all it cares is the frequency of a word, or how often a word is used, then TF-IDF is a very simple, quick, fast approach to go with. As long as you don't take, as long as your vocabulary size is not too big. Yeah, somebody's asking, how do we get the vocabulary size? Yeah, it just does word tokenization. It splits the word. It splits the like goes through each sentence in the entire document or entire corpus. It tries to get the unique words and uses that to build the vocabulary. Did I answer your question? I thought I saw a question pop up. Is it Michael? Okay, cool. So it's no magic here. Everything here is like really good. Now, let's do something nice for this. We can do something very nice, and it's going to help us. So you guys can see how we can apply TF-IDF into stuff. We're going to do this. Oh, Kathy, how are you doing on time? We've
actually run out of time, but let's do the demo. I'm sure we all came here to learn. So
okay, cool. So take a look at this, right? And I want to build this with everybody. So I'm going to try to build like a very simple, kind of like a very simple classification program here, right? So we're going to classify something as that and this as that. It's going to be very simple. So you look at this sentence. This one talks about natural language. This one talks about, it involves understanding. This talks about natural language, for example. This one talks about AI and machine learning. So let's do this. Let's build an algorithm where labels. And remember, the computer wants and zeros. So the plan I'm having right now is if I have one will mean I'm talking about NLP. And if I have zero will mean I'm talking about AI, like, or not NLP, right? It could be like generic, right? Not NLP, something like that. So for the first one, I would treat it as 1. For the second sentence, I would treat it as 0. For the third one, I'll treat it as 0. And the last one, I'll treat it as 1. So let's say I wanted to build like a classification based on this to make it work. Let's pick some of the classifiers from sklearn. So we can pick, let's see, sklearn. Let's pick naive Bayes. It's fine. It's like one of the, let's pick multinomial. It is based on the naive Bayes algorithm. Let's not worry about that. Like right now, there's a bunch of like models you can look at, or a bunch of training stuff you can look at. So, and then let's pick sklearn. Let's do a model selection, and let's do, so we will split this into training and test so we can work with it if you want. And then let's see if sklearn can give us a metrics. Let's see this. What's the metrics? The one we need for this is accuracy score. Great, cool. So let's do some slides training. So we use TF-IDF because we've already created like a vectorizer here and pushed already. So we already know what's happening here. Cool. Now, when you are doing the training, or when you hear people talking about the training, they try to put them into like a vector, right? An X and a Y. The X is your inputs, your Y is your prediction. But what we are trying to do with the machine learning bits that I'm going to show extra as using TF-IDF is we are going to assume that we are going to be training based on this. Don't worry, we may not have a better accuracy. You'll see. We're going to be training based on this. So with machine learning, what you're trying to do is you are trying to figure out the algorithm, but you are using your input and output. And normally you flip the whole thing and say, this is my input. Let's write some algorithm and let's make sure we can get the output always. But in this case, we take our input, we take our output, and then we figure out the algorithm in between. And the algorithm can be used for other things, right? Once it becomes that. Your X is your inputs, your Y is what you currently have, and then later we'll figure out some prediction based on that. So we are going to have 4 things, right? We'll do an X string, and I'm going to use small cases just for now. We'll use an X text because we will split whatever we have into like 2 sets. And then we'll have our Y train. Let's see if this works. So we are saying that we have, make this the next line to make it easy for people to see. So we have, start from here. We are saying that we are going to split this into 2 groups. We're going to split it into like 80% for the training, 20% to test. So if you have 4, 3 of them, if I'm getting my math correctly, is going to train, and 2 of them, so I got 4, 3 of them is going to train, and 1 is going to test. So we just check to see that the model is like good and same. And instead of using the bag of words, we are going to use TF-IDF because we need that matrix that we built. We need that to work because remember that we cannot train with just words. So we need to train with numbers, right? With numbers for the computer. So we have now converted everything. We're using the TF metric that we built here, which is exactly its conversion. And the labels has to match. So if there are 4 items here, I need to have 4 there as well. And that's why I made sure this is also like an array of 4. 1, 2, 3, 4. Yeah, matching all that. So now that we have this, we can now start creating this. So let's see if I have a classifier, and I'm going to use a multinomial one that I have. And I'm going to do my classifier, and I'm going to fit my training. So I'm saying for these inputs, these are my matching outputs. They have to be the same side. Don't worry about these details today. Maybe next time we'll take a look at how to write these in from scratch. It's just to show us how it works. And then I'm saying, okay, try and take the test ones, make predictions, and give me what the Y will be if I were to be on the matrix to say what's the predicted ones, just to kind of like figure out what's happening. And then I can figure out accuracy score by calling the accuracy score and saying, okay, I tested with this. Oh, sorry. I tested with, I think I have my Y test where Y test is here. And then I have my Y prediction. So I'm like, yeah, take a look at this and build on top of that. Okay. And then I can print my accuracy with classifier just to see how it's working. Cool. That's it. It's not saying 0. Yeah, it's fine. It's fine because we didn't initially like train pretty well. We have just like a 4. But we could have trained with something and it could tell us like 1 or 2. Sorry, 1, 0 or 1, depending on where it's going. It's just going to make sure that if we were to give it some sort of prediction, we had like our own text. Let's say we had it in this one as our test, and then we would say, tell us what it's going to be, and it's likely going to give us 1 if we were to test that. I'm not going like that far, but that's the key thing of what we're trying to do. The point is, I cannot feed my model. I cannot feed this with text data. I need to feed it with numbers. And for me to get the numbers, I need to figure out how to represent the text data into numerical formats that I can use and I can process it. I hope this makes sense. We'll spend some time to get this in and probably get this accuracy to 1 if you want. There are more advanced versions of feature engineering. There's like the word embeddings one. So there's the one from I think Google, the word2vec. I can show you how it works. And then there's a one from I think it's Stanford called Glove. and we can take a look at that too. And there are advanced versions of word embeddings where you can give it an entire document or entire corpus, and it will learn the relationship between words. And that's different from these two that I just showed. These are like basic, simple, but there are more advanced ones that will figure out that I think king and queen should be closer because they all talk about the royalty as a concept, right? Well, I think that and that should be closer in value because they all relate to something very similar. And then we will go through some of those details. So let me summarize what we've just gone through. Text data is unstructured, it has stuff. We can't just work with it. We did some basic Python stuff just to help us with playing through it. Very simple. We realize that we need to clean up text. There are stuff on text that you may not necessarily want, so you may want to remove them. One of them is stop words. We talked about stemming, we talked about lemmatization, and then we talked about regular expressions that you could use as well if you want, right? You can do your own stuff if you want, or build your own stuff. Then we talked about tokenization, which is about taking the text inputs and breaking it down into something you can work with. It could be you're breaking it down into words. It could be you're breaking it down into sentences. Or it could be you're breaking it down into characters. Or you could even be doing subword level, right? Breaking down to subwords if you want. And then we also realize that even though I have those tokens, I can't work with them because they are text. So for us to actually use them, we need to get them into numbers. And there's about two ways to do that, right? So one way is to use the bag of words. Okay, I can convert everything to a bag of words using the count vectorizer. You can use different libraries with their own ways of calling them, but it's still like a bag of words about them. And then we can see the entire bag, right? You can see the entire vocabulary set that is used, and it represents everything in 1 and 0. Then we did the TF-IDF, the term frequency approach, where it's like improving that by figuring out weights or trying to assign weights to numbers with respect to the frequency in the context with the entire document. And then we went through all of that. We discussed like some of the cons with that approach, and then we did like a rough sketch, like algorithm that takes in the 10 frequency metrics and uses that to train a very simple classifier to work with. But yeah, I think the classifier is saying the accuracy of it we can work, but we can look at the prediction and then we can give us stuff as well. Okay, so I can also do this. Right, it will tell us what it's predicting. So that scenario, I think it's predicting 1 there as well. So it wasn't that bad. Cool. Anything? Any question? Any question, concern? Okay, Audrey.
Are the weights assigned for the TF-IDF? Is this based on the frequency of the word or its relation to another word? Are there some criteria or factors that influence the weight?
Okay, so I didn't hear clearly, but I'm going to guess. So I'm guessing the question you were asking is for the term frequency in this document frequency, TF-IDF, how does it assign the weights? Okay, so there are some stuff that I know, and I can tell you that one of them is that it assigns higher weights to words that are particularly significant, right? If a word is less important, it means they will appear very often. Like the word "the" is in a huge document would appear so often that they lose their meaning. Such words, based on the algorithm, often ends up with lower weights, not 0, but lower weights. The main thing with TF-IDF is that it's capturing the frequency of a word in a document, right? Like, for example, in its context, like in its sentence, as well as within the entire like corpus. There's some if you do for smaller kids like the one with them, you don't see it very well. It looks like it's repeating, but it's very effective if the corpus or the document size is really large. Like let's say I gave it an entire book, then it would make real sense because the words that will come up with 0 weights will be the ones with like low, we don't have to pay too much attention to it, and the ones with the higher weights, I mean, they are either rare or not, or like they are either rare or they have a higher meaning with respect to the entire document. It's able to figure out that, like, if you do it for like larger corpus. Cool. Yeah, but larger corpus will be a problem because you need like high compute. You need to store and get the entire dimension for like all the based on the vocabulary of the document. That could be like very large. So yeah, there are better ways to do it. Like that. But it works if you need something very quick. Any more questions? Okay. Cool. Sounds like everybody's happy. That's good. If there are questions later on, I can pull up. Oh, Susie, do you have a question?
Yes. So whilst going through, I realized that there are some existing data that we use, like for instance, the filler words, and then the and stuff. So let's say you want to, let's say there's a new language, it's a remote part that you want to build an NLP for. How will you go about it?
Yeah, so that's something I had planned to talk maybe in the future about. So there is a whole concept of what we call language modeling, right? And in language modeling, there are two aspects that you want to figure out. So one of them is you either want to understand the language or you want to be able to go through the ChatGPT approach of like replying to stuff. But you would need to start modeling the entire language in one way or the other. There are other tools. One that I like so much for some of these modeling stuff would be like Spacey. So Spacey will allow you to create a very minimal language model that knows how to determine parts of speech and a few of them. And then that could help solve some of the tasks in there. If you're also solving the problem of, let's say, figuring out embeddings, right, or meanings behind words. Let's say you have like there's a different language, you build FAQs in that language, and you want to build these AI solutions that kind of like checks a question, picks the right area where that whole thing is, and then work it out. Then you could also try to create your own embeddings library. So you'll have to feed one of those, and maybe next time I'll show you guys how to train like some sort of a small word embedding library. But you have to train word embedding libraries with a lot of document in that language, a lot of information, so you can at least understand the nuance or the details between the words, right? And if you think word embeddings are not good, then you need to go down to subwords. Just trying to figure out how you can get some sort of embeddings on the subwords, and then it understands the language. Then the next step will be to do something similar to what OpenAI is doing, or something similar to what Google with BERTs, one of those BERTs variants are doing, which is you then make a decision that do you want to predict the next word, or do you want to predict the context given one word, or giving some context with a word missing, do you want to predict that word? And you're going to train a number of them, like if you have like you pick your like a flow. Once you have that train, you will have something similar to what the language models are doing right now. It might be like an SLM, like a small language model. Does that help you, Sosu? It's a lot of information, but it takes time to get there.
Yes, that helps. Thank you.
Yeah, we can do small stuff, but for you to get to the ChatGPT level, we could even build a GPT-2. At least I know how to do that one. GPT-2, not GPT-3. I still don't have the details of GPT-3 yet, so I can't. But the GPT-2 has been published, that we can talk about that. Right? But before you understand some of the expressions or things you use at that level, you need to first build the basics of NLP. So you understand how NLP is built, how it's designed, used to solve simple problems, and then it just gives you the intuition you need to tackle those advanced concepts, to pick a paper and start implementing them. Cool. Any more questions? You guys are good? Okay. I'm assuming everybody is good. It was a pleasure trying to talk to you guys about this. It's very complex, and I'm sorry if I wasn't so clear with some of the explanations, but if it was helpful to you, yeah, next time we will improve on that.
William, are you wrapping up? It was really great.
Yep.
So what are the next steps? Okay,
Yeah,
Audrey raised her hand. She has a question.
yeah, sure, shoot.
Hi, I'm really appreciative of the lessons that we've had, what we've learned so far. The question I have now is not quite related to the material, but the whole setup. I want to understand what group is organizing this, how it came about. This is a series that continues. I just saw the link today and then I registered. So I'm not quite sure what the plan is, and I'm quite interested. So I want to know more about it.
I think that's for Kakwe.
Yeah, that question is mine. Okay, so Kraado, there's a link here called Kraado, kraado.co. Please visit the website and go to the community part. So Kraado is in twofold. We have the business vertical and we have the community vertical as well. So for this particular session, it's a free session for university students, recent graduates, and people switching careers into tech to learn skills, whether they are newbies or they are in the middle or they are seniors. So an opportunity for people to interact with people who are working in specific fields in tech. That can become your mentor or your coach. And for the coaching sessions, we charge a fee. Some of them are sponsored, some of them are a small token just to keep the community running because the Quadro community is run by volunteers. And some of the volunteers are myself. So Sue, even William himself is a volunteer because he's donated most of his time coaching people. Yeah, so William has taken a new track, which is NLP. He's interested in AI related stuff. He doesn't like it when I say AI, but that's the language everybody uses. So he has accepted to become the AI coach for the community. Yes. So if you want to continue, we'll have other sessions. But then because of the availability of these resource persons, we space them out. I don't know when he will be available, but you can follow him on LinkedIn. Definitely join the Crado community on WhatsApp, and you get to know all the feature programs we have. We also have our videos on YouTube, so you can catch up on things that you missed. And if you want something specific related to your career in tech, just reach out to me once you join the WhatsApp group. And then when you DM me, I can connect you to the right coach. And then that's it. We'll set you up for success.
Wow, that's amazing. Thank you, Prado. Thank you, Williams, and every other volunteer. I'll definitely follow up.
All
And
right. Yeah, thank you so much. I'm also glad you are very engaged. Can you tell us a bit about yourself? Are you a student? What are you?
um, I'm not a student. I graduated last year, 2024. I did biomedical engineering, and I'm currently working. I'm doing my national service with a research institution. We are doing digital health projects, so AI in healthcare, and I'm still finding my feet. Yeah, so that's what
Okay.
I'm doing.
Yeah, what's most important is getting a place to practice what you learned in school and also building upon your skills, having that growth mindset. So you are at the right place. And William, if I had given him the chance, he could have gone for 6 hours. I have experienced that myself. So he will come back again. You just need to avail yourself and have lots of data. Yeah.
And you
Okay,
made a
so
mistake.
this is what we call it a day or an evening. William, thank you once again. And thank you, Susu, for moderating. Thank you, Victor, for working behind the scenes. Till next time. Bye, guys. Bye,
Thank you.
ladies.
Bye.